3 billion emails are sent every hour, and nearly half of them are spam. If we look at this email, we immediately realize that it is a spam email. But how does the machine realize it? An email has thousands of words, and each word changes the probability of it being spam or not spam. Checking how these words relate to each other is computationally impossible. We need to make a naive assumption to solve it. This assumption leads us to one of the most effective classifiers, the Naive Bayes Classifier. Let's first understand what Naive Bayes Classifier is, and then we will move on to the code to try this with an example. And how do we handle the new words that are not present in the input dataset, followed by the strengths and weaknesses of this classifier. It is a probabilistic classification algorithm based on Bayes' theorem. It predicts the class of an observation by calculating the probability that it belongs to each possible class, then choosing the class with the highest probability. For classification, we want to find the probability of a class given the features. If we consider an example of spam detection, we need to find the probability that an email is spam given the words it contains. Here is the formula. In this formula, probability of class given features is the posterior probability. This is what we need to find. The probability of features given class is the likelihood. How often we see these features in this class. Probability of class is the prior probability. How common is this class overall? And probability of features is the evidence. How common are these features in general? Now comes the naive assumption, the key simplifying assumption. The classifier assumes that all features are conditionally independent given the class. This means that knowing one feature doesn't tell you anything about another feature, as long as we know the class. For spam detection, this means that the word free is independent of the word money given that we know it's spam. In reality, this may not be true. Words like free and money often appear together in spam emails, and that's why it's called naive. This assumption makes the math simple. Despite this assumption, this classifier works well in practice, especially for text classification. Let's walk through a simple example to see how this works. We start with just 4 emails, 2 are spam and 2 are not spam. And the first step is to calculate the prior probabilities. The probability of an email being spam and not spam, irrespective of the words within it. These are our prior probabilities, the baseline probabilities before we even look at any word. And the next step is to count the words. This is to understand how frequently these words are present in spam emails and not spam emails. Now it's time to calculate the probability. Let's take an email which contains the words urgent free money. We need to find the frequency of these words in the input dataset. If we notice, the word urgent is not present in the input dataset. So, the probability of word urgent being spam is 0 and the same for not spam as well. Now, if we try to calculate the probability of this email being spam or not spam, we get 0 probability for both the classes. And we are unable to classify this email. How do we resolve this issue? The answer for this is Laplace smoothing. We add 1 to all word counts. This is called add 1 smoothing or Laplace smoothing. This would ensure no word is left with 0 probability. And in denominator, we add the total unique number of words in the vocabulary. And we can classify whether the given email is spam or not spam. We are calculating the product of probabilities to determine the class. The issue here is that the more words we have and the words with less probability, the product of these probabilities tends to be near 0 and it might be difficult to determine the class. To resolve this issue, we could take the log of the product of probabilities, which would be the sum of log of individual probabilities. Let's try to classify another email using a log of probabilities. We start with calculating prior probabilities and log of it. Then, for each word, we calculate the log of probability of being spam or not spam. We predict the email as spam. This simple example shows the entire process: calculate prior probabilities, count words, apply smoothing, use logs, and compare probabilities. In reality, we may need to process the data before we train the model. Let's take a slightly bigger dataset with 30 emails. 15 of them are spam and 15 of them are not spam. We pre-process the text by converting to lowercase, removing punctuation, and splitting it into words. We build a vocabulary of all unique words. We calculate word probabilities for each class using Laplace smoothing. We create a classification function that takes an email, extracts its words, computes log probabilities for both classes, and returns the class with higher probability. We test it on new emails. Emails with words like free, win, money, urgent, and click get classified as spam. Emails with words like meeting, tomorrow, report, project get classified as not spam. We can visualize which words are most indicative of each class. Words like free, click, win sit at the top of spam. Words like meeting, tomorrow, thanks sit at the top of not spam. We validate our implementation by comparing it with scikit-learn's Naive Bayes Classifier. Both produce the same results. The key question remains: why does this work despite the naive assumption and ignoring the dependency between the words? Even though words are not truly independent, the classifier still works well because it's comparing two options. It doesn't need to get the exact numbers right. It just needs to rank spam higher than not spam for spam emails and not spam higher than spam for legitimate emails. Naive Bayes has 5 key strengths. The first one is it is simple and fast, easy to implement, train, even with large datasets. And the next one is it works well with small training sets. Unlike deep learning models that need millions of examples, Naive Bayes can work with just hundreds. It handles thousands of words easily. With thousands of words in a vocabulary, most classifiers struggle, but Naive Bayes works well. It gives us the probabilities, not just yes or no. This is useful when we need confidence scores, and it ignores less important words. If some words doesn't help tell spam or not spam, then they don't hurt the classifier. But it does have limitations too. The independence assumption means it cannot learn how words relate. It won't learn that free money together is more spammy than just free or money. It needs smoothing to handle new words. Without Laplace smoothing, a single new word can break the classifier. The probability it gives, while useful, may not be perfectly accurate. The order may be correct, but the actual values might be off due to the naive assumption. Naive Bayes has many applications beyond spam detection. The first one is sentiment analysis. For example, is this movie review positive or negative? Document classification, like which category does this news article belong to? And medical diagnosis, given these symptoms, what disease it is most likely. Real-time prediction systems. Because it is so fast, it is used in production systems where speed matters. The beauty of Naive Bayes is in its simplicity. It takes a complex problem, makes a bold simplifying assumption, and still delivers excellent results. It's a perfect example of how sometimes the simplest approach is the best approach. In our Python notebook, we implemented this entire pipeline from scratch. We pre-process the text, calculate all the probabilities, build the classifier, test it on new emails, visualize the important words, and compare it with scikit-learn implementation. We also explore the mathematical foundation in detail, showing how Bayes theorem transforms into the classification rule, how log probabilities prevent numerical underflow, and why Laplace smoothing is necessary. But we are just getting started. Naive Bayes treats every word equally, but the word urgent carries far more information than the word the. How do we measure the importance of words mathematically? How do we quantify information itself? The answer for this is entropy, the math of surprise. And it changes everything. That's what we are going to see in the next video. If you prefer reading, a link for the detailed companion blog post and Python notebook used is in the description. If this video helped you understand Naive Bayes Classifier, hit that like button and consider subscribing to continue to decode the complexities of machine learning. I will see you in the next one.